Welcome to Analysis 1. This course is part of an online math program with the goal to provide a video resource for people who would like to supplement to their formal course in school or just to teach themselves extra mathematics. So first of all, let's ignore the 1 over here and just ask the question, what is analysis? Analysis is the branch of mathematics that, very generally speaking, studies how functions behave and how we can do calculus on them. But that might seem a very quote-unquote trivial thing for someone who just took calculus. But actually, there are many more things that we can do with calculus. For instance, real analysis, which we are going to learn in this course, studies a rigorous version of single variable calculus and multivariable calculus, and some people call them vector calculus. It's actually the same. So it studies how we can rigorously build a foundation on the calculus of functions with a real variable with input and a real variable with output. And when we went to this is what we do in analysis 1, and in analysis 2 we will look at how to build a foundation for multivariable calculus, so multivariable functions, which goes from a vector with length m, taking real values, and to Rn. And in complex analysis, we are going to extend that into functions which took a complex number as an input and complex number as output. So after that, we'll actually learn more real analysis, but this is slightly different, and I would not be explaining that right now. It's not very much like the calculus that you have been seeing for your past life. So I'm just trying to give you some idea. There's also things like Fourier and harmonic analysis, which is the study of decomposed functions into waves. All I'm trying to say is that analysis is a very rich subject. It's not just some subject that's trying to make calculus rigorous. Okay, but that's still the goal for analysis 1 still. And let's just skip the question why analysis here and first ask the question, what are the prerequisites? So the only prerequisites, as labeled here, is single variable calculus. You need nothing other than that. And right, now let's go back and ask the question of why analysis. Because after you got familiar with the practical tools of limits, differentiation, integration, and power series, you might think, well, that's all. But actually, when we learn freshman calculus, usually the emphasis is to say how you compute this thing, and how to, for instance, how can you compute the area under a specific curve? How can you compute a certain volume of revolution? How can you use that to solve physical problems? But those rules are presented to you in a rather intuitive and almost obvious way. And they let you repeat those rules many times without telling you that those rules has a lot of restrictions. And some of those restrictions are emphasized. For instance, you can't use L'Hopital's rule on the limits of the form, like for instance 1 over infinity, stuff like that. You can only use them on the infinity case or 0 case. But that was not, but there are actually a lot more exceptions like that. And the goal for this course is to outline those exceptions and actually build the entire calculus theory rigorously from start to end. And the goal for every concept that you are going to encounter this course, how are you going to master those concepts? Well, you need to first understand definitions, and then understand some correlated basic results, which are theorems or corollaries. You don't need to memorize all of them. Some of the theorems, after you learn them, you will soon forget them because you do not use them very much. However, some results are very important, and you should definitely understand and memorize them. And also, for each theorem, at least you need to being able to give a sketch of the proof after spending some time trying to recall how to prove it. It's definitely okay that you don't remember all the proof, but at least you should have some idea what are general steps or general strategy I'm going to apply in reconstructing the entire proof. And then most importantly, as I said, is that you should be able to tell the restriction of certain intuition. This course is not set to completely break your intuition. Right. So intuition is still relevant. It's just that, as Terence Tao, a very famous mathematician, said, analysis is the subject of ruling out the wrong intuition. It's not the subject that asks you to abandon your intuition completely. So through formal logic and a lot of counterexamples, we'll be able to enhance our intuition, and then as we proceed in further mathematics learning, it will be very helpful. Great. So first of all, let's come back to the question of why we bother learning analysis. So very ironically, as I just said, this course is not about abandoning your intuition. Still, I'm going to break what you think is a very intuitive things to do. And first of all, let me just give you an example. Suppose that we are going to sum the following array, which has m rows and n columns. So a11, a12 up to a1n, and vertically we have a21 up to amn, and then we have those elements labeled in the following way. We got amn. Suppose we are going to sum the array. One way we are going to do this is that we first go horizontally. So for a fixed row index, we sum over of the column index, which is j. So j goes from 1 to n, and then we just add up of the rows. So I goes from 1 to m. And the second way, of course, is to sum over of the columns first, and then sum over one particular column and go over all of the columns. So it's just equivalent to switching the order of summation. Right, this is absolutely true in the finite case, because we know from elementary school that addition is commutative. And so identify the following claim as true or false. Suppose we have an infinite array, so a11, a21, go on and on and on. And we have here a12, and on and on and on. And suppose that now we are summing from I equals to 1 to infinity, j equals 1 to infinity of aij. Is that equal? Still, like, is switching the order of summation still relevant, still true? Well, if you answered yes, then you're absolutely wrong, because a counterexample can be easily constructed. So for instance, if I write down the array this way, just give me a second. So you have 1, -1, and then on the second column, you have 0, then 1, -1, and then all the way 0. On the third column, you have 0, 0, then 1, -1, and 0. And then on the fourth row, you can have 3 zeros, and then 1, -1, da da da. And then when you sum this thing, if you first sum of the rows, and then you sum one particular row, and then you add up all the rows. And what you will find is that on each row, the sum is equal to 0. So for each particular j, you have aij, I goes from 1 to infinity, is equal to 0. So what does this mean? This means that if you sum over all of the I on top of that, you still got 0. However, if you sum horizontally, so you fix an I, and then sum over all of the j's, on the first row, you got 1. On the second row, you got 0. On the third row, you got 0. On the fourth row, you got 0, etc., etc. So what will happen is that you are summing over all the row and you got 0 except the first row and you got 1. So the result is 1. So now, obviously, this trick in this case is not relevant. So but obviously in some cases we want it to be relevant. Because this is a very useful trick. Sometimes summation over one index is easier than summation of another index. It's just like if you took multivariable calculus, we realize that sometimes switching order of integration makes the entire integral from a monster to something that's very trivial. And right, so now the natural question is, when is this true? When is this valid? When is this switching, switching order of summation valid? And then we can ask many similar questions. So there are also a bunch of counterexamples which are actually more involved. I promise I will present to you in later lectures, but in this lecture, I will not go in depth. It turns out that you might encounter the idea that a function converges to a series of functions converge to another functions. For instance, if I define a series of functions that looks like this, then you will realize that as n goes through for each fixed x, as I let n tends to infinity, this function eventually tends to 0 for all of x, and therefore therefore this function will tends to fx equal to 0. Just to give you some idea. So then we might ask a natural question. If I got a series of functions that converge to a particular function f, if I took the derivative of this series of functions, does that necessarily converge to the derivative of the limit function, like the function converge to? Well, it turns out that the question is not always yes, although that you might think it is. And similar things applies when we first took integral of a function, a series of functions, and then take the limit. It might not necessarily be the same if we first took the limit of a series of functions, then took the integral. Right. So the idea is that the process of switching several familiar signs might not be relevant in certain cases, and our goal is to figure out when are they relevant. And just to give you one last example for those of you who took multivariable calculus, is on the topic of switching orders of integration. So for instance, if we got a multiple integral, well, for those of you who only took single variable calculus, it's okay, you can skip this. So it seems like, because this integral you can interpret as follows. You can establish a three-dimensional coordinate system, x, y, and z, and basically on the point xy, you go up the z coordinate and you find the point where z is equal to fxy, and then you can visualize the functions, right? And for instance, if the functions look something like this, sorry for the poor drawing, I'll try to improve later on. And then you can interpret, if you integrate over this rectangle, you can interpret the entire integral as calculating the volume under the surface. So you got a small volume. Let me try my best drawing. So you can calculate this strange volume. And order of integration, geometrically speaking, is just fixing one variable and integrate over another. So slicing across slicing parallel to the YZ plane, slicing parallel to the XZ plane, right? And because the volume should be fixed, so the order of integration shall not matter. It seems like so, at least. So maybe we will think that it is always true that the double integral of fxy first integrate with respect to dy and then dx must be the same as fxy first integrate with respect to dx then dy. But it turns out this is not true, and I can actually give you a not so involved example. So let's consider this integral. So the idea is that we first integrate it just this way. And what we end up getting, I will leave this as the process and exercise for the viewer who's learned multivariable calculus on their own. This is just 1. But however, if we switch order of integration, so we first integrate with respect to dx, and then dy, let's not worry about dy first. What we end up getting is that e to the negative xy, where of course goes from 0 to infinity. And what we end up getting is 0. So when we integrate it again from 0 to 1 with respect to, sorry, I'm out of space here. Let me move this around. Then dy, then we got one more integration to do. I will not bother writing the bonds. We still end up getting 0. So by switching order of integration, we got 1 is equal to 0, which is not true. So the switching of integration order does not always apply. Right, I promised you that I will give you more examples involving some usual examples of how calculus rules we always being taken for granted are actually not true, such as switching the order of summation and integration when we got a power series. Or many other exceptions. So one last example on one of the most famous and well-liked theorems by calculus students, L'Hopital's rule. So you might recall that this very little nice rule where you can turn the limit of the quotient of two functions into the limit of the quotient of their derivatives. And you might also recall, if you still do, that it can be only applied if you either got infinity on both the numerator and denominator, or you got 0, 0. However, even in the case where you got 0, 0, this rule might not apply. Let me just give you an example. For instance, if you consider the function of x squared sine to the negative 4, x to the negative 4 power divided by x, you'll see that the numerator goes to 0 by squeeze theorem, and then the denominator also goes to 0. And okay, so the L'Hopital rules shall apply, right? So let's just keep computing. We got x goes to 0. And then if we, there's a bit of mess in differentiating this, but let's just do this. And you got minus 4 next to the negative third power cosine x to the negative fourth power, and then the numerator is easy, denominator is easy, it's just 1. And then okay, So let's see, what is this? Well, the first term by squeeze theorem goes to 0, but the second term, there's something weird. The second term does not go to 0, and actually the limit does not exist. The reason is that because x third over 1, this term, will blow up to infinity very, very fast. And cosine x to the fourth is a function that's oscillating, and an oscillating function times an infinity function, we can kind of imagine that is, well, we can actually prove this, but I'm not going to discuss the proof. It's just that this oscillating function does not control this exponential functions which goes to infinity. What end up is that this entire thing does not tend to do anything. It's just a function that's jumping up and down and with larger and larger magnitude. Right. So I just went to Desmos and plot this function for you. So you can actually see that this function, as x becomes very small, so this function 4 times cosine x to the negative fourth power divided by x to the third, and when you multiply 4, it's the same, so I didn't write the constant in Desmos. You can see this function oscillates higher and higher and does not approach anything. So you should be still convinced that this function does not converge as x goes to 0. Okay. And this is pretty much for today. And thank you for watching, and I'm going to list a few references I will be using throughout the entire course. So first of all, one reference, which is my favorite analysis book for an introductory level, is Understanding Analysis written by Steven Abbott. I'm not sure if I pronounced the name right, sorry. The second book is by Terence Tao, called Analysis 1. He actually wrote another book called Analysis 2, and we'll be using that in the future, so better reference that. And I will also be using a little bit of Walter Ruding, which is a classic called Principles of Mathematical Analysis. Ruding is a lot more involved on an abstract level, and the book is rather concise, and personally I don't think it's a text that's meant written for an introductory level course, so I will not be using it a lot, but some of the content's still great. For example, how we construct real numbers, and I will be referencing some of the point set topology from Ruding too. So those are the 3 textbook resources I'll be using. There are also a lot more lecture notes, which I cannot recall at this moment, but any useful resource, I will try to post them in the comment section. And thank you for watching, and I will see you in the actual real lecture.